right. We're now going to cover 8.3, which deals with multiplying, dividing, and simplifying radicals. And we've kind of already seen a little bit of this. So first, let's kind of write down the two rules that we're going to be mainly dealing with. And that's that if you have the nth root of a times the nth root of b, or in other words, as long as you have two roots that are multiplying together, and those roots have what we would call the same index, or they're the same type of root, both square roots, both cube roots, both fourth roots, what have you, then it turns out that you can write this as one root where the insides are multiplying and then perform that multiplication. And we've actually seen this before because we exploited that a little bit when in the sections before we had something like, I don't know, the square root of 4 ninths. What we did was we kind of did this rule in reverse. We said, well, you can just square root each part of the fraction individually and then let's put them back on top of each other where they were. So 2 is the root of 4, it was in the numerator, keep it in the numerator. 3 is the root of 9, it was in the denominator, keep it in the denominator. So it's kind of that rule in reverse, but this is the, of course, division rule and not the multiplication rule. But again, the idea here is if you've got two distinct roots or different roots, how do I say it? Roots of different values that have the same index, then by all means multiply them together in one root. And then same idea, if you've got the nth root of a divided by the nth root of b, then if you have the same type of root, why not write that as one root and then a, b? We kind of use that in reverse here. We said, well, I started off with some fraction that I couldn't clean up somehow, so let me separate them and combine. But we're going to see in this section, 8.3, that sometimes we want to go the other way around. We have two individual things that don't look nice together, but when we include them in one fraction, we can maybe do some simplifying. Or when we have multiplication, we can do some simplifying. And so that's what's going on here on this first example. The first example would say, hey, you have the square root of 2 and the square root of 50, and you're multiplying them. Why not find the square root of 2 times 50? Because according to our rules, we can do that. Well, that's 100, and 100 just writes, or roots rather, to 10. All right, and now we're going to start to get some interesting stuff here. Let's see what goes on here. I'm going to already start to clean up my multiplication as I go. So in other words, I now have the square root of 100 because that is 5 times 20. And then I'm also going to have, careful about our exponent multiplication rules, n to the 5th times n to the 7th, we'll have our exponents add and we'll get n to the 12th. And we're starting to see some combined ideas. So 100 roots to 10 and a exponent of 1/2 when I have something to the 12th is going to divide. I'm going to end up with n to the 6th. And it says assume all variables are positive, but actually the n to the 6th would force anything to be positive anyways, so no need for absolute values, but that might make a comeback from 8.1 as we're in 8.3. Up next, this one's not going to be nice, but hey, that's the root of 77. Now, that's the idea, is 77 doesn't root nicely at all. You can check for yourself. It's going to be some really ugly decimal. How do I know that for sure? Well, because unfortunately, as a math teacher, I've memorized some perfect squares, and I know that 64 is a perfect square, I know that 81 is a perfect square, and there's nothing in between. So anything from 64 to 81, or anything between 64 and 81 is not going to root nicely. All right, up next, this rule, there we go. All right, now this time I've got a cube root situation going on here. So just to say out loud, we can multiply 5 and 25. These are the same types of roots. So I am going to have the cubed root of 5 times 25, which happens to be 125. If you take your calculator out and use all the skills we've used prior, maybe write 125 to the 1/3, maybe write math cube root 125, it turns out that that is 5. If you want to see a fancy way, or maybe another intuitive way of knowing that that is 5, you could think about it like this. Well, 5 on the left, there's only one 5 there, but 25 is 2 5s put together. So in other words, when I've got the cube root of a single 5 and the cube root of 2 5s, well, I now have the cube root of 3 5s multiplying together. Or in other words, I've got the cube root of 5 cubed, and those cubes and cube roots cancel and I just get 5. So just another way of saying or seeing that. All right, this one could get maybe a little bit interesting. It says they want an exact answer, so that is a square root. Now I'm multiplying fractions, so when you multiply fractions, 11 will multiply to the 7, numerators multiply together, denominators multiply together, and 77 and 6 have no common factors, so that is as simple as it gets. All right, now here we are using that rule in reverse, kind of what we did right here. 9 roots nicely to 3. 64 roots nicely to 8. All right, now things get a little bit interesting because 11 doesn't root nicely at all. So I am going to have a fraction, but 11 doesn't root nicely. And the idea is, this isn't the final answer, but remember that if you've got a single fraction, you could split this into essentially 2 roots, still with a fraction. But the idea is 11, again, does not root nicely, but 49 does. So this would actually be a more simplified version. Root what you can, and what can't, well, just keep it inside of the square root. All right, this one we're going to simplify. So the idea here would be to write this as a single root, so we'd have 14 over 7. But of course, then the idea is, well, 14 over 7 actually does divide, and it divides to 2. Unfortunately, 2 doesn't square root nicely, so we'll have to keep it in the square root. All right, now it's time to use a calculator because I do not know what 336 divided by 7 is. Turns out it's 48. All right, so we get the square root of 48. Now I also think, and let's just double check, I don't think that's going to be the final answer because I know through time and practice that 48 at least has a 4 in it, and 4 is a perfect square. So there's probably some way to break this down. And let's just check. Yep, exactly. Your answer in 48 can be simplified further. So in other words, I do have the right answer, but it's not fully simplified. So what's going on here? First, we had 2 distinct roots in a fraction. So we put them inside of one root and then did the fraction division. We got 48. But now that we have 48, we're going to go like the opposite route. We're going to say, well, wait, 48 has a 4 in it. What would I be left with? I'd be left with 12. And actually, let's think about that a little bit further. Wait a minute. 12 also has a 4 in it, which is a perfect square. So really, 48 is 4 times 4 times 3. I guess I'm going to prefer to write that as like 16 times 3. All right. In other words, I've now found the largest perfect square. And the way I did it was, here's kind of, we'll write this a different way later, but I kind of said, well, I think 4 is the largest perfect square. And then I happened upon 12 as the other thing I need to get 48. Well, then I said, wait a minute, 12 is a perfect square. And there are my 2 perfect squares. Now, depending on what you read or watch on other YouTube videos or textbooks, usually what people will do is they'll actually like take these out and you'll have a 2 and a 2, but I kind of prefer to say, well, if I have all my perfect squares, why don't I just multiply them together? Because it turns out that when you multiply perfect squares together, you get perfect squares. Or in other words, it's kind of easy to look at this now and go, oh, well, 16, or let's use our rule, now that I'm multiplying, 16 roots to 4, and 3 doesn't root nicely, so keep it in. So I always prefer to find the largest perfect square by maybe thinking small at first. You know, maybe you don't know that 16 times 3 is 48. So maybe you don't know that 16 is the largest perfect square. That's okay. You can start small, so to speak. You can find 4 and then see if anything else shows up. And then by multiplying all your small perfect squares together, you'll always get the largest in the end. So anyways, our answer is 4 square root 3. And we're doing great on time. All right, and actually this prep exercise is just, reminding you the same thing, that this might have a perfect square in it. All right, let's see here. So now we're going to explain why this isn't in simplest form, and it's actually kind of the same idea. We're going to dive into a new-ish topic here, and that is that we're trying to third root something. So we're trying to third root something, but the exponent is 5. Or in other words, we have an improper fraction. So, improper fractions are called improper. It's usually not right to have the numerator be larger. Or in other words, it's kind of weird to cube root something that's larger than a perfect cube. We should maybe take that perfect cube out, or we should maybe take the extra whole number, so to speak, out. And we'll investigate what that means later. But that's the idea. X to the 5th has a perfect cube as a part of it. There's just 2 extra things left over, because 3 and 2 make 5. Okay, so simplify by factoring. We're just doing the algebra here. Once again, 50 has a perfect square in it. It has 25 in it. So we can break 50 up into 25 times 2 and split them into individual roots because 5 does square root nicely and 2 does not. And we've got the same idea here, only this time there's a 4 out front. I am going to kind of cheat a little bit because I just dealt with 48 earlier. I know that 48 is really 16 times 3. And there was a 4 out front. So here's the 4 out front. It's still there. 48 broke down to 16 times 3. Well, 16 roots to 4, and 3 doesn't root nicely. But now I've got two outside numbers to multiply, but I'm ready for my final answer. I get 16, square root 3. And here we go. It's time to put algebra into the mix. This is a tricky section. Again, the idea is think about improper fractions and maybe mixed numbers. So what's going on here? Well, we've got multiplication going on. We've got x to the 10th, essentially times y to the 4th, times z to the 14th. And remember that this square root is an exponent of 1/2. So we've got 10 to the 1/2 times y to the 4/2 times z to the 14/2. And it also says we can assume that they are all non-negative, so we don't need to worry about any absolute values around them. But well, 10 over 2 is 5, 4 over 2 is 2, and 14 over 2 is 7. And there we go. One very important point to make, and this is going to show up later in 8.4 and so on, is this kind of just using that square root on each exponent is only possible when all we're doing is multiplying or dividing on the inside. If there were addition or subtraction signs, there would be a lot of different stuff going on here to try to simplify. But x to the 5th, y squared, z to the 7th. All right. And now things are going to get really, really interesting as things just get uglier and uglier. I wonder how many more do we have to go? Well, we're almost there. We're doing okay on time. Okay, so up next, we have an r and an s squared that are just tagging along outside. And now I'm going to already kind of exploit some rules we've seen before. I've got an r to the, let's see here, 13 over 2 because we're square rooting. And we've got an s to the 5 over 2 because we're square rooting. Okay, here's what I'm going to do. I'm going to say to myself, well, 13 over 2 doesn't come out properly, but here's what I can do. I can essentially write this as a mixed number, or I can say, well, 13 over 2 comes out to 6 completely and 1/2. All right, so how many 2's are inside of 13? There's 6 of them, and you're going to have 1 left over as a remainder, and you were dividing by 2 before. So same idea, how many 2's are in 5? There are 2 2's inside of 5, but there's, again, a remainder. So how can I clean this up now? They also want me to use radicals as needed. So in other words, they don't want these fractional exponents. Well, here's how I can clean this up. I now have some essentially like whole number exponent r's. I've got an r to the power of 1 and an r to a power of 6. Because we're multiplying, those exponents are adding, and we've got an r to the power of 7. For the s's, there's an s squared and an s squared, and again, we're adding those because those bases are multiplying. And now we've got some leftovers. We've got an r to the 1/2 and an s to the 1/2. And so, again, using exponent rules, we could say, well, that's r times s to the 1/2. Or in other words, that's the square root of rs. Okay, that is our final answer. And we'll write this out in a few different ways to explain this concept further. Square root of r and s inside the root. Make sure you get the r and the s inside the root. All right, so let's look at this example. There's only one variable this time. So we've got y to the 22 over 3. Again, let's think about this like division. How many 3's can go inside of 22? Well, 7. And how many are left over? Well, 3 times 7 is 21, so there's a remainder of 1. All right, now another way of writing this out, and this is kind of complex, is you could think about this like this. You could say, well, I'm really taking the cube root of, and let me see how many perfect cubes I have. There's a y cubed, 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 and then one y left over. So there's the 7 perfect squares, or how many times does 3 go into 22? So 1, 2, 3, 4, 5, 6, 7 of these get pulled out as an exponent. And then there's one left over that was not a perfect cube, and that's the one that gets stuck inside of the cube root, because again, we have y to the 7th, that's a whole number exponent, but that 1/3 means cube root of y, the one that did not escape. All right, these 7 escaped and they're multiplying together, so 7 y's multiplying together are now outside, and that's y to the 7th, and one of them did not escape. So far, we've only seen remainders of 1, or in other words, just a single index as the exponent left over. That's probably going to change in the next example or two. I've done something weird. There we go. Cube root y. And I'm going to go ahead and stop this one, and we'll finish this up in a part 2.